This is part 6 in a series of videos in which I am repairing this third Wren computer. In the previous videos in this series I've gone through some initial repairs on this board. It's had a lot of faults and it still has a few issues. This is the point where if you're not careful it's easy to kind of get distracted and disillusioned with electronics. So if you haven't repaired a board like this, then my only advice really is to persist with it and use it as a learning experience. These are a lot of fun to play with, they're a lot of fun to work on, certainly a lot of fun to use once they're working. But as we go through this, you'll see that there are some real pitfalls in dealing with machines of this vintage, especially machines like this that were really pushing the boundaries of what's really feasible. The issues with this now are not just simply failed ICs. In fact, most of the ICs I've replaced that have improved things up to the point where we can at least boot to the menu screen on the Wren have not been ICs that have failed. Most tested fine in the IC tester, but it comes down to something I've said quite a few times in my videos about the way that IC performance degrades over time. So in order to progress with this board, which I'll come back to in a few minutes, there was a change I wanted to make to it simply because of some of the parts I had to hand. And I thought, as I've been asked to show more detail in the testing, I'd just demonstrate why I'm making this change and also what the advantage in the change is. I'm not modifying the machine as such, I'm just swapping some of the parts out for a bit of an upgrade. And they are the main system DRAMs. So these are 150 nanosecond devices. I had some 120 nanosecond devices. They wouldn't cure the problems I'm having, which I'll explain why later in this video, but I just wanted to explain how you can go about making this change if you want to attempt it. Now, I've already explained in previous videos using the Fluke to do various testing, such as bank switching, testing the RAM by writing values to it and reading them back. Okay, so if we look at the data sheet for these DRAMs and we look at the pinout, you'll see that pin 1 is shown as not connected. But more importantly, the address lines only run from E0 up through A7, so there's only 8 address lines. So that, if you're not familiar with DRAMs, you may wonder how this device can be a 64K bit device. And the way this works is the two lines, RAS and CAS, are used as latch strobes. One's for the row address and one's for the column address. So the way this device is operated is the row or the column address is put onto the address lines, latched in, so that gives you 256 possibilities, and then the opposite. So if you latched in the row, you follow that with a column, and that gives you 256 times 256 possible permutations. So that's how we can address 64 K bits using just the 8 address lines. But what you often find in machines like the Wren and all well-designed machines is that they allow expansion of the DRAM, and the way they do that is they fully decode all the address lines. And in this case, although it's shown as not connected for the devices that are installed here, and these are 64K devices, we should find that bit 1, or rather pin 1, is actually being driven if we select a different bank. So I mentioned that the memory in this machine is banked, and we've been looking at banks 4 and 8 for the ROMs, for example, bank 0 for the DRAM. But we should be able to select other banks, and I suspect that banks 0, 1, 2 and 3 are all DRAM banks, because the user manual for this machine says that it can support up to 256K of RAM. So I'll just move the camera across so that we can see the display on the fluke. Okay, so we've got the scope in the background and we've got the fluke, and as I've shown before, if we want to select a different bank, we just write a value to port 0, which is the bank number that we want, so we'll select bank 0. If I now put the scope probe onto pin 1, which is not connected for these particular devices, you'll see that we've got ground or no signal on the scope. But if I select a different bank, so if I select bank 1 for example, we can see we're now getting data showing on the unused pin of these DRAMs. If we select the next bank, we can see we're getting a different pattern. So in other words, this machine seems to be fully supporting the entire 256K of RAM. In fact, it won't give us 256K because the upper 4K in all the banks is common, so we'll get 60K in each of the 4 banks plus the 4K at the top. 244K if we fully populate this with 256K DRAMs, or at least that's the theory. So we'll give that a go. Just to prove that this is going to work, what I'll do is try writing values to each of the banks with the 64K DRAMs fitted. So I'll reselect bank 0. So we've got bank 0 selected. We'll try writing a value of 1 to it. So that's our first bank. So I want to write to address 0. We'll write a value of 1. We'll read that back, and it's 1. I'll change the bank to bank 2. So when I look at bank 2, we'll read back the value we've just written, which should be in a different bank, but because we've got 64 DRAMs fitted, they're all occupying the same memory space, so they're all really duplicates of the same memory, so we should get the same value, and indeed we do. We can write to this, but it's writing to the same banks. If I try writing to 0, in fact I'll write a different value, so we'll try writing 2 and read that back, we should get 2, which we do. So although it's reading and writing back when we select different banks, we're actually not selecting a different bank within the RAM, we're just looking at the same RAMs in each bank. So what I'll do, I'll swap the 64K DRAMs for 256K DRAMs and see if we can in fact write different values to each of the 4 banks. Okay, so I've swapped the 64K DRAMs for 256K DRAMs, and the only difference in terms of the pinout is that on the 256K DRAMs, this is still the 64K DRAM spec sheet of course, but the difference would be that pin 1 would be shown as A8, and that gives us access to the full 256K of addressable space within the DRAM. So what I should be able to do now is select any of the first 3 banks, and that should give us access to what we now should have as 4 separate DRAM banks, albeit they're in the common devices of course. So we'll just make sure that we've got bank 0 selected, and we'll write a value of 1 to that bank at address 0. We'll read that back, and we've got a value of 1. We'll now change to the second bank, so this is our second bank value, and we'll try reading address 0, but notice now it's not showing a value of 1. If we go back to bank 0 and read address 0, we're still getting a value of 1, but if we switch to bank 2 or bank 1, it starts at the number 0 through 3, and read that again, you can see it's a different value. So we can now, in theory at least, write to this bank, so we'll write to address 0 again, but this is address 0 in the second bank, and we'll put a value of 2 in there. We'll now switch to the next bank, and we'll put a value of 3 in there. And finally we'll switch to the third bank, or bank 3. And we'll write a value of 4. So if we now read this back, so I'll read back, we're getting 4 in the third bank. I'll start from the beginning and read the first bank, and if we read that, we're getting 1. Switch to the next bank along, and we're getting a value of 2. Go to the next bank, read that one, that's 3, and then finally, so as you can see, we can now write different values to address 0 in each of the 4 banks. So in other words, we now have a 256k machine instead of a 64k machine. CPM, which is what this system runs when it's booted the operating system, has a BIOS call that when it's reading and writing memory sets the bank. So in theory I suspect that the Wren fully supports this, and it will allow CPM to access the 256k of RAM. However, the reason I made this change wasn't to give me more RAM, it's because these RAM chips were faster. And I'll get the fluke out of the way and we'll move back to the PCB and have a look at it, and I'll start to explain what the issue is that I'm having with it. Okay, so looking back at the Wren, it is currently booted up. See, we've got the welcome screen, and it will boot from floppy disk, but it's really behaving in a flaky manner at the moment. I had hoped to move on and start demonstrating the software that came with the Wren, but at the moment it's just not running reliably enough to do that. The other 2 machines are working quite well, they're reasonably stable, but this one is really being a pain, and there are still some issues I need to resolve with it. Since the last video when I showed it running on the fluke, it stopped booting from floppy disk, and I traced that to a couple of failed ICs over here, and once I'd fixed those it started booting again, but again it was operating in a very flaky manner. It would run and then it would crash, and then it would run and then it would crash again. And this is kind of typical of machines of this era once you start getting ICs that begin to degrade. And I've mentioned this before, and in fact if we put the scope probe onto a couple of the key points, so this is one of the data buses, you can see that the quality of the signal on there is extremely poor. If we put it onto an area where the signals aren't too bad, you can see that the signal amplitudes on these areas are much higher. The signals are much clearer. You can see, although it's I won't do a single capture, but you can see that the rising and falling edges are much steeper, and the values that are retained by the signals are reasonably high and reasonably low. But when you look at this particular bus, you can see that the signals, especially you can see one here, is looking extremely poor. And it looks like there's a failing IC, but all the ICs that are attached directly to that bus have been replaced. So that this is the video data bus, so this is the shift registers that shift data out into the display, the multiplexing latches and buffers, the character RAM, and the main buffer onto the main data bus. They've all been replaced. So I suspect what the problem is here is there's a race condition going on with regards to the control pins on these devices. and so that their access is overlapping, and that seems to be the case. I think I mentioned before that one particular buffer is getting very hot, so there's some contention going on the board, and it's not just as simple as it being a failed IC. Just to further explain what I mean by this, I've made a very simple garbage schematic here just to try to explain the principle. Let's say we have two signals coming in and the edges occur at exactly the same time. So it's a rising edge, it occurs exactly the same time. Now ignore the levels on here, it's the timing I'm interested in. I haven't bothered inverting them, I want to keep the explanation as simple as possible. But let's say that the output of this circuit is a time critical event and we have two outputs, and let's say there are signals going to a RAM chip, for example, and there is a maximum time between one edge and the other that's allowed for the system to work. On a very slow system, it doesn't matter, they'll be fast enough to keep up, but as you increase the clock speed, then the amount of deviation between the two edges that's allowed before the system will crash or start to have problems diminishes. And so if we take a circuit like this, you'll see that we start off with two signals that are directly in sync with each other. We go through the first gate and we get a delay caused by the propagation of the first gate. So now the two signals are no longer truly in sync, and so by the time we get through to this point, we're already out of sync. So there are two delays on one of the signals and only one on the other. We go through another gate here, so we end up with the same one propagation delay skew here. We have another gate here, so we end up with even more of a skew. Now when the devices are new, when the board's first made, that may be fine, but as the devices age and they start to slow down, then this skew we're getting at the end is going to start to increase to the point where the board may stop working. Now in addition to that, this particular gate has much greater fan out than this one. So this gate is driving 1, 2, 3 other inputs, whereas this one is only driving the one. So again, as this gate starts to age, its output performance will start to drop, and that's going to increase the skew even further. So what tends to happen as the board starts to age and all the devices start to age, if you're getting too close to the performance and propagation performance delays introduced by the devices, then at some point the board's going to stop working, or it'll start randomly crashing or doing strange things. And that in turn can lead to ICs being damaged when maybe two are being switched on at the same time that shouldn't be. And I suspect that's what's going on here. It's a case of trying to track down which ICs I need to change to get rid of this poor behavior that the system's exhibiting. None of the devices seem to have failed. If I slow the clock speed down, then it will work to a certain extent. It won't work properly because certain parts of the board, especially things like the floppy drive interface, expect certain delays and speeds to be adhered to. So I can't just simply slow down the system by putting a slower crystal in, it wouldn't work. However, what I have been doing as part of testing, because I need to be able to boot it to do any real sensible investigative work. I don't have a schematic, so I can't simply start tracing the circuit through. What I have to do is try to figure out where the issues might lie, what may be causing this skew, so I'll work back from devices that don't seem to be working properly. But it could be something that's not directly accessible to the microprocessor. As I said, this is a very advanced system, so it has a DMA mechanism built into it, which as far as I can tell, I haven't fully reversed it yet, but as far as I can tell, it's some buffers and counters that are used to allow the floppy drive controller to directly transfer data in and out, bypassing the Z80. And I think it generates an interrupt when it's finished doing that, but it means that that mechanism isn't coming through the Z80 socket, so I can't just fully test that using the fluke. and it's that sort of thing that's likely to be causing this errant behaviour. So to try and track this down, what I've done is, as I've mentioned previously, I put a socket in for the crystal. So I pop the crystal out. This lead goes up to a signal generator. Just point the camera at that so you can see. So up there we've got the signal generator. So I have it set to 12 megahertz, but it allows me to modify the duty cycle. The duty cycle is important in timing issues with a system like this. If you've watched my videos on the transistor microprocessor, then I mentioned that when I was designing that processor, I had to take into account all the various timing for each of the major blocks to make sure it would operate correctly. And the same thing is true here, and I mentioned at the time that duty cycle is very important for the system to operate as it needs to. Now this board will only run if I set the duty cycle to 40%. If I set it to anything else, it will just crash. It will crash anyway if I start trying to do too many things with it, but at least it allows me to get it running so I can start to investigate the various signals. So that's where I am with this. The reason for replacing the DRAM, of course, was to try to remove that as being an issue. The other reason I think this is some weird timing problem is it will only work with a Z80A. If I try and put a Z80B in it, it will not run, which is kind of strange because the A is only rated up to 4 megahertz, whereas the B should go up to the full 6 megahertz, which is what the clock is that's being fed to it. So I suspect that when I put the B version of the processor in, it's kind of overtaking whatever's causing the problem and causing the system to crash. So it's going to be an interesting one to sort out. I need to try and find out why it's having issues. I suspect it's a slow glue logic chip that's causing this, but it's going to be an interesting and fairly tricky one to track down. With a schematic it would be tricky. Without a schematic it's going to be a real trial. So I'll keep posting videos on this. If you've got any ideas, or if you want to see more detail of all this testing, then please leave a comment.